Right, our discussion obviously today focuses on complex numbers. Complex numbers, now, for example, in this case, we are effectively saying let Z be 5 minus 2i and W be minus 4 minus 3i. We need to find some of these real parts, like the real part of the product of Z and W, but also we need to find the imaginary part of the multiplicative inverse of Z. Okay, so we look at the solutions to these particular questions. And first, solutions. Right. Now, solutions to part 1 and part 2. Let's focus first on part 1. Right. So part 1 focuses on the real part of the products or the real part of ZW. Right, so I know that much of this is something possibly you know, and this is therefore the real part of Z. What is Z? Z is 5 minus 2i. So we're just revising some of these things. Right, 5 minus 2i, and then W is minus 4 minus 3i. Right, is minus 4 minus 3i, and we close like this. And this is what obviously the real part is. Okay, let us just perform the algebra here. So we're going to multiply using the normal multiplication of binomials. 5 times minus 4 gives us minus 20, and 5 times minus 3i gives us minus 15i, and minus 2i times minus 4 will give us plus 8i, and minus 2i times minus 3i is going to give us exactly minus 6. Okay, now let's carefully obviously look at this multiplication, and most importantly, we need to make sure and to ensure that we really are getting the correct products here, and we're not really making any mistakes. Okay, and then now obviously simultaneously I'm just checking the multiplication to make sure that our multiplication is very, very correct. I don't want typos here, but obviously in the end we're interested in the method, but we must make sure that we avoid mistakes. Okay, so this is what we have. Now let us continue then. This is the real part of minus 20, and minus 6 will give us minus 26. Minus 15i plus 8i will actually give us minus 7i, like so. And therefore, if we're supposed to find the real part, so the real part is actually minus 20, minus 26. Okay, that is the real part, and the real part is the part without the I. Okay, so in other words, we can conclude and say, for example, hence the real part of ZW is minus 26, and this is the result. Right, this is the result. Okay, but we
Hello?
could, yes, please.
Can you explain this symbol?
This symbol, okay, this symbol means the real part. So in other words, this symbol, as it is written here, let's speak about the real part a little bit. Okay, I'm just going to get back to the presentation. All right, there's something called the real part. Right, so obviously the real part of a complex number. That's what we're talking about. We're speaking about complex numbers. So the real part of a complex number. So in other words, the real part of a complex number Z, for example, will be the real part of the complex number Z of the form x plus iy, and the real part is x. All right, so now we have just extracted the real part there. Okay, and so at this point, we have extracted from the complex number we got the real part, and the real part is minus 26, and that is what we have written down. Right, so we continue to look at more properties of complex numbers. We're interested in finding the imaginary parts as well, because given a complex number, we can be able to find the imaginary part. At this point, where we are asked to find the imaginary part of the multiplicative inverse of the complex number Z, which is 5 minus 2i. Let's look at that one. Right, so that is Number 2, we're asked to find the imaginary part of the multiplicative inverse of z. In other words, the imaginary part of 1 over z, and therefore it is the imaginary part of 1 over, and this is 5 minus 2i. Okay, that's what we wrote here. That's what we wrote here. It's 5 minus 2i. All right, let us find the imaginary part of this. So the imaginary part of this is the imaginary part, which is 1 divided by 5 minus twice I. We multiply by 5 plus twice I. We divide by 5 plus twice I. And this multiplication is multiplication by what we call the complex conjugate. So this entity here is called the complex conjugate. So we discuss complex conjugation. Now, if this is the complex conjugate of, in other words, the complex conjugate of a complex number is that complex number whose imaginary part has the opposite sign. If it is a minus, then we actually put a plus, and if it is a plus there, you put a minus. So that constitutes what you call the complex conjugate of a complex number. Just to mention, the idea of a complex conjugate is a very well understood concept. Z equals x plus iy is a complex number. This means that we can find the complex conjugate shown by z conjugate or z bar, which is x minus iy, like this. Okay, so this is complex conjugation. Now, with that mentioned, then we're able to compute here and find the imaginary part of this. So 1 by the numerator is 5 plus 2i. Right, the denominator is clearly a product of this with that. This product here is like what we call the difference of 2 squares. So 5 by 5 gives us 25. Then we just multiply the imaginaries, the imaginary parts. Minus 2i times plus 2i would give us plus 4. And therefore, this means we have the imaginary part of 5 plus 2i, and we divide these by 29, which is 25 by plus 4. Okay, let's do this one. Sorry. In other words, now if we have the imaginary part of this number, imaginary part of this number, number 2, the imaginary part of the 1 over z. Okay, let's just start there to be more systematic. So we have the imaginary part of what we just got here, which is 5 plus 2i over 29. 5 plus 2i all over 29. And this is the imaginary part of 5 out of 29 plus 2i over 29. Right, and therefore now we're interested in just finding the imaginary part of this number. And what is the imaginary part of this number? The imaginary part of the number is 2 out of 29. And obviously we're able to therefore say thus the imaginary part of 1 over z is 2 out of 29, and this is the result. Okay, so we have found here the imaginary part of this complex number. So yeah, take a particular note of this, and this is extremely important for us. And we shall obviously discuss a little bit more examples.
Hello?
Yes, please.
What happened here?
Okay, what happened? That's a good question. What happened was that we extracted the imaginary part because by definition, okay, if z is x plus iy, then the imaginary part of z is just y. So the imaginary part, we just take the coefficient of I. So here the coefficient of I is 2 over 29. So the imaginary part of this will therefore become 2 out of 29. Now, there's certain things that remain extremely important for us as we discuss complex conjugation. Right, so in other words, we take just a couple of notes. Right, note, if z is x plus iy, and we agree that This is the case where Z is a complex number, but X and Y are real numbers, like this. Okay, then if this is the case, then we make the following notes. Then the real part, okay, let me just write it in words. Right, so then the real part of Z, right, is denoted as what? Is denoted as the real part of Z, which becomes the real part of X plus IY, and this real part is X. There's something we call the imaginary part. The imaginary part of Z. The imaginary part of Z is the imaginary part of X plus IY, which is the imaginary part is just the coefficient of I. And then there's something we call the complex conjugate of Z. Right, so the complex conjugate of Z is X plus IY, and therefore its complex conjugate is X minus IY. Okay, so these are some of the properties that we shall learn very much into. But there's something also we call the modulus of Z, the complex modulus of Z. So what we call the modulus of Z. Just call it the modulus of Z. Right, so modulus of Z. Right. Z is X plus IY implies that the modulus of Z is the square root of X squared plus Y squared. This entity is called the modulus of Z, or, well, I mean, we study, or what you call the absolute value of Z, but yeah, we call it the modulus of Z. Well, the absolute value is normally for real numbers. Okay, so we take note of this, and this is the actual distance. The actual distance of the complex number from the origin. A complex number is that sits in the first quadrant of this. This is called the argand. It's called the argand diagram. What is the argand diagram? Well, the argand diagram is the complex plane. Right, argand diagram represents what we call the complex plane, and it's very important we note this. Now, the complex plane is drawn in many ways. For example, now this one is the real part of Z, okay, which is normally called the x-axis, and this one is called the y-axis. Or obviously, then we are able to plot the complex number like this. A complex number that sits in the first quadrant, for example, will therefore be of interest to us. Yeah, but it doesn't matter where the complex number sits. So whether the complex number sits in the first or it sits in any part, like any number, like any point, you can plot, because this complex number is like a point. But this complex numbers themselves can be viewed as vectors, and therefore we're able to find the distance from the origin to the complex number, which is this one. So in other words, we are able to, so this is a result that we learned in school, a result after Pythagoras. So yeah, we take note of this. So this one is going to be y, and this is going to be x, for example. This is going to be right angle, and the length of this here is, the length of the hypotenuse is this entity here. Okay, now there are a couple of things that remain very, very important to us that we need to take note of, and I want us to pay particular attention to these. And so now, for example, we're expected to have knowledge for our assessment of the following things. Right. Here is one, evaluate. Right, so evaluate, for example, 1 minus I to the fourth power. Right, we need to be able to evaluate 1 minus I to the fourth power. And how do we do 1 minus I to the 4th power? Okay, so this one we use what we call Pascal's triangle. Right, so to do the solution for this, something we call Pascal's triangle. Okay, right. Pascal's triangle. What will Pascal's triangle tell us? It tells us that a triangle can be formed like this. If you add 1, 2, you get 3. 2 and 1 you add, you get 3. You add 1 and 3, you get 4. 3, 3, you add them, you get 6. 3 and 1, you get 4. You have 1, 1. Okay, because this one is to the 4th power, so this one will be associated, for instance, with the expansion x plus yi to the 1st power, and this will be sort of the coefficients. And this one is going to be the square. This is going to be the cube, and this is going to be the 4th power. Right, so x plus yi to the 4th power. Okay, let's just evaluate this one, where the coefficients, therefore the binomial coefficients will be 1, 4, 6, for 1, just an example. So, but we can do cubes and squares and higher powers. So let's just do this one. For example, the y minus I to the 4th power. By the binomial theorem, we start by the coefficients first, and you can see the coefficient is 1. So we're going to put 1 times, we raise this one to the 4th power. Then the next thing is we put a 4 plus 4. Then we cube the 1, and the minus I now will have power 1. Right, and then there's 6, because it's 1, 4, 6, 4, 1. Then there's 6. The 6 we square. The minus I now will increase in power, because it was power 0 here, power 1 here, power 2. And then now there's 4, which is going to be 1 to the power 1 minus I to the 3rd power. There is coefficient 1 according to the Pascal's triangle. Then we come here, the 1 is going to be to the power 0, and the minus I is going to be to the 4th power. And this means if you have this one here, we have the following. Right, so when you come to this now, this is 1 is 1. And then here is minus 1 minus I. You raise to the power 1, but there's a 4 there. And this is going to be minus 4i, like this. And this one, you square. If you square minus, the negative is going to be a plus. But you square I, you get a minus 1 times 6, which is going to be minus 6. And now this one here, you cube it. If you cube I alone, it becomes minus I. Right, so if you cube the minus I, so you're going to be getting just I, right? So which is going to be plus 4i. And then now you raise this one. So this one now you raise minus to the 4th power. Negative raised to the 4th power is what? It's just a 1, and you raise I to the 4th power. It's like I times I times I times I 4 times. But I squared is minus 1. So there are 2 I squareds here giving us a minus 1 times minus 1, which gives us a 1. Okay, so in other words, we have 1 minus I to the 4th power. So yeah, okay, now clearly here you have these two guys, and 1 and 1 gives us 2, and 2 minus 6 gives us minus 4, and this is the answer. Okay, just some complex operations that we must be able to perform. Okay, here's another example. Right, so if Z is 5 plus 2i, and W, right, and W is equal to what yeah, can just take the same thing here. Right, W is equal to, yeah, okay, 5 minus 2i minus 4 minus 3i. Okay, 5 minus 2i minus 4 minus 3i. Right, like so. And then now, okay, if this is the case, find the modulus of Z the modulus of W and the modulus of ZW, for example. Okay, very easy stuff. Just practicing here. So obviously, I'm sure that this will be pretty straightforward. Let us find the length or the modulus of Z. Okay, so Z is this one. So its modulus is 5 minus 2i. You find the modulus and you find the square root of 5 squared plus minus 2 squared, like this. So by definition, you square the real part, you square the imaginary part, and 5 squared is what? Is 25, and minus 2 squared is 4, and this is the square root of 29, like this. Okay, now we can do the same for the other one. Okay, let's just, W, for example, will be minus 4 minus 3i, minus 4 minus 3i, and then you have the square root of minus 4, you square this, and minus 3, you square this, and therefore if you square minus 4, you have a 16 with a 9, and therefore this is a 25, and therefore the square root of 25 is 5, so that the length of the modulus of this, which is the length of the vector, okay, complex numbers of vectors. So yeah, we can always discuss that because every complex number can be perceived as a vector. Okay, with this mentioned, then we're able to state some of the properties that are very important that we need to know. For example, okay, for purposes of study, I want us to also make mention of the abbreviations of this. Okay, let us find this one, for example. If W is 3 minus I, find the imaginary part of 1 over W. Right, so we need to expect these kinds of things. So let's quickly look at the solution to that and practice, and then we shall move on to domains and other things. Okay, now let us look at this. So to find the marginal part of 1 over W, we're going to say the marginal part of 1 over W is the marginal part of 1 over W is 3 minus I, like this. Okay, and therefore, what is this? It is the marginal part of 1 over. So this is 3 minus I. We perform complex conjugation on the 3 minus I, getting 3 plus I. We divide by the same thing. So this is multiplying by the conjugate in that manner. Okay, getting now the marginal part of the numerator will be 1 times this, which is 3 plus I. And then we divide 3 by 3. It's 9. Okay, this is like a difference of 2 squares. Multiply 3 and 3, the minus I and the plus I, so they give us together a 1, so that the marginal part is 3 plus I divided by 10. Okay, so for example, now if you have a marginal part of 1 over W, so it is exactly the marginal part of 3 plus I out of 10, which is the marginal part of 3 out of 10, I out of 10, right? And the marginal part of this complex number is 1 over 10, right? So, and we are done with that particular kind of a problem here. Right, and I want us to find the following, and this is very important. If, for example, if Z is 1 plus 4i, find the length of the complex conjugate of Z. Right, so now, how do we do this? First and foremost, we need to realize that we need to find the length of the complex conjugate, which is the length of 1 plus 4i, like this. And therefore, if you find the complex conjugate is 1 minus 4i, the length, the modulus, is 1 squared minus 4 squared. And therefore, this here is exactly 1 plus 16, and this is the square root of 17. Okay, you need to check these yourself, because, well, you need to check the instructions for the assessment, because, yeah, it's very important that because normally you need to type in the answers. So when you type in the answers, now some of these are decimals, like this one is going to be, I gave it on purpose, it's going to be the square root of 17. So the question then obviously at this point becomes, how does the system take the answers and what answers does it accept, because it was rejecting answers at some point. So 4.12310 is the square root of 17. But now the question is, how can that system take the responses? Because there are many ways in which one can type in this answer on a computer assessment, computerized assessment. So you can do SQRT 17. Okay, SQRT 17 is obviously is irrational, but you'd have that it is approximately this. But now the question is, what do you type? Do you type SQRT 17? You need to check the instructions. That's my point. The instructions before the assessment is started, so that you can, because you can get the right answer. And now if you type SQRT 17, because you need to type in the answer, and that assessment does not have characters, does not have these symbols where you can just punch the square root and it appears there. Okay, so it's something that you need to take note of. I want us to discuss certain things that are called domains and ranges. Right, so as part of what you need to know what a domain is, but also you need to know what ranges are. And let us discuss these very, very important things. Now, what is a domain and what is a range? So you must be able to perform certain sketches. Right, sketch. Sketch the following. Sketch the following sets and determine. Right, and determine which are domains. And determine which are domains. Now, let us look at this one. Z minus 2 plus I is less or equal to 1. 2, B, the modulus of 2Z plus 3 is strictly greater than 4. C, you have the imaginary part of Z is strictly bigger than 1. D, you have the imaginary part of Z is equal to 1. E, okay, there's something we call, okay, no, right, there's something we call the argument. Right, so you have the argument of Z, which is less or equal to pi over 4, where Z is not 0. And then you have F. Yeah, I've split the meeting into a couple of parts, into 3 parts. Okay, so we shall have that. So now let us first look at some of this. Let's look at the first one. Now we need to sketch these particular sets. Let's sketch part A. And then obviously our time is going to elapse. I'm watching the time there. We still have more time. But now when the time elapses, then I'm going to start the next session immediately in like 15 minutes there. Okay. And that's how I plan to do today's discussion. Yeah, but it's going to be in the end 2 hours, or after all 40 minutes each. Right, Z minus 2I plus, no, minus 2 plus I. Right, so it's minus 2 plus I modulus, which is less or equal to 1. Okay, so we have this here, and to sketch this is easier to note that Z is a complex number, so we let Z to be X plus IY, so it has also a real part X and an imaginary part Y, imaginary part Y. So you have minus 2 plus I, and you have less or equal to 1. Okay, within the modular sign, and you can group the real parts, which are x and minus 2. And then now you just pull out I here, and you have the imaginary parts that are like two of these, two imaginary parts. We factor out the I, and then now we can take the, okay, what is the modulus? The modulus means the square root of the square of the real part and the square of the imaginary part, and the result is less or equal to 1. Okay, so at this point, if you have for part A, the square root of, for example, x minus 2, you square this, and then y plus 1, you square this. Okay, and then now we have less or equal to 1. Okay, you square both left and right. You square both sides of this. If you square both sides, you have x minus 2. You square that, you have y plus 1. You square that is less or equal to 1. Okay, so this kind of geometry, a geometrical representation, it has so the extreme. Okay, so this is a set, or this is the set of points inside and on the circle centered at the point right, sorry, it's centered at the point 2 minus I. Okay, this is positive 2, and this becomes like a minus 1, 2 minus I. So yeah, or we can take it from here. And at this point, we can write this as z minus, but then you put 2 minus I, you factor out the negative here. And so obviously this becomes z minus 8 is equal to 1, where this is a complex number. So this becomes in general the center associated with this circle. And this is some radius. Yeah, but yeah, once again, this is not a circle, it's a region. And obviously, in the way this is described, this is the set of all points inside and on the circle centered at the point 2 minus I, okay, with radius 1, right? So with radius 1, okay. Okay, but now very important. So we're describing the kind of set. Describe the set. This is a set of points inside and on the circle centered at the point 2 minus I with radius 1. Okay, it is not. It is okay, let's first describe what it is. It is closed. Okay, because if you sketch this, it's gonna be like this. A circle is like this, and it has the center there. But now it's equal to 1, so the boundary is included, but it's less, so you also shade the interior. In other words, it is closed and bounded. Right, it is closed and bounded. It is the set of points inside and on the circle centered at the point 2 minus I with the radius 1. It is closed and bounded. Okay, it is closed. Why is it closed? Well, a set is closed if its complement is open. Okay, that is 3. This module is connected to 3.7 is real analysis 3711. Okay, so that is where you get the definitions on real sets and so on. Okay, now, so but is it a domain? Is it a domain? Because it is closed. So okay, we're going to discuss. So I'm going to give a formal definition of a domain, but we're going to say it is not. it is not a domain. It is not a domain as it is not open. Domains in mathematics are open. So it is not a domain. Okay, so why is it not a domain? As it is not open. How is it not open? Okay, because it contains a boundary and also the interior. It contains the boundary and also the interior. So this one here is closed, but also it is bounded. And hence it is not a domain. All right, I think that this is very much enough. We discussed a little bit, but we're going to return again in 15 minutes. Okay, so I'm watching the time now. Okay, we could take a short break. So we're going to return again at 4. You forgive me because I'm going to split the meeting into 3 today. But we shall return again at 4. I'm going to send another link closer to the time, because sometimes it's, you see, it said the link was invalid because I sent it a little bit earlier. I think that the might be expiration, the time, and all that. So yeah, I mean, like 5 minutes before, I'm going to send the link. And then now we're going to continue at 4 p.m. and we're going to look at more things, a continuation of this. Okay, but yeah, I'm going to make this video available for you to just pass through and check the discussion. But I'm going to bring new stuff that you need to know for the assessment. Okay, yeah, bye for now, and thanks a lot then. Thank you. Goodbye.
Should I leave?
Yes, please. Yeah, it's okay. It's okay for now until 4. Until 4. Shall meet again at 4.